Here I will have a speech about my chapter reading and comprehension. In this chapter, firstly, we look at how to develop Cuda kernels using a profile-driven approach, allowing us to optimize our code based on real performance data rather than guesswork. Next, we dive into the nature of warp execution to understand how threads are grouped and scheduled on the GPU, which is crucial for writing efficient kernels. Following that, we discuss strategies for exposing more parallelism to the GPU, ensuring that we fully utilize its computational resources. Next, we explore grid and block configuration heuristics, learning how to choose the right dimensions for optimum performance. We also examine important Cuda performance metrics and events, helping us identify bottlenecks and measure improvements. Lastly, we probe dynamic parallelism and nested execution, powerful features that let kernels launch additional kernels on the GPU itself. Next, I will showcase each demonstration of the code example provided by the textbook and each exercise implementation. In each code example and exercise, I will compare the performance in the console log, and I also will use the insight system to probe the stats of execution performance between different functions. This code demonstrates Cuda's nested kernel execution capability, where GPU threads can launch new kernels directly from device code without returning to the host. When execution begins, each thread displays its recursion level, thread ID, and block ID, providing visibility into the parallel execution structure. The algorithm implements a recursive pattern where only thread 0 from each block launches child kernels with half the thread count, creating a binary tree-like execution hierarchy. As each nesting layer completes, diagnostic messages show the execution depth, allowing us to trace the nested kernel flow. The recursion continues until the thread count reaches 1, at which point the deepest level terminates and the control bubbles back up through the layers. This dynamic parallelism feature enables the GPU to create work on demand during execution. Unlike traditional Cuda programs where all kernel launches must originate from the host CPU, the compilation requires special flags, -RDC and -L Cuda divert to enable the device runtime library that supports nested kernel calls. The running example here is nested Hello World 2. This creates 2 blocks of 8 threads each, showing how the recursive execution pattern scales across multiple blocks with decreasing thread counts at each nesting level. The nested reduce code demonstrates parallel reduction using Cuda's nested kernel launch capability. Device threads can recursively spawn child kernels to perform some reduction operations. The implementation compares 3 approaches: CPU recursion reduction, traditional GPU reduction with neighboring pairs, and a novel GPU nested recursive reduction that leverages dynamic parallelism. In the nested approach, which is here, each kernel level performs in-place reduction by adding elements with a halved stride at each recursive step. Only thread 0 launches the child kernel with half the threads to continue reducing the array. The algorithm uses Cuda device synchronize inside the kernel to ensure that all child grades complete before proceeding. This creates a hierarchical reduction tree where each level halves the problem size until reaching the base case of 2 elements. This approach eliminates the need for repeated host device synchronization points required by traditional iterative reductions. The entire reduction hierarchy runs entirely on the GPU. The nested recursion continues until only 2 elements remain, at which point they are added together. The result then bubbles up through the recursion levels to produce the final sum. The running example here process 4 blocks of 128 threads each, demonstrating how the nested recursive reduction scales across multiple blocks while maintaining the logarithmic reduction pattern at each level. Nested Reduce 2 code file explores different ways to implement parallel reduction using nested kernel launches. We have 4 GPU approaches here. First is the traditional neighboring pair reduction. Nothing special here. Then we go into the nested kernels. The main one is GPU recursive reduce. It does in-place reduction first. Then thread 0 launches the child kernel with half the threads. Key point here, it uses Cuda device synchronize to wait for child kernels to finish. This ensures correctness but adds overhead. Next is GPU recursive reduce no sync. Same idea, but removes the synchronization. This is faster but potentially unsafe. Race conditions can occur. The last one is GPU recursive reduce 2. It uses a different strategy. Only block 0, thread 0 launches children. All blocks participate in each level. This creates a different execution pattern. The beauty of nested kernels is simple. No host device round trips. Everything happens on GPU. Each level spawns the next level. Reduction tree builds itself. The algorithm keeps cutting the problem size in half. Eventually, we reach 2 elements and just add them. Results bubble back up the recursive chain. The running example here tests A blocks with 256 threads each, comparing all 4 reduction methods to show performance differences between synchronized and unsynchronized nested approaches. Nested Reduce NoSync file focuses on optimizing nested kernel reductions by removing synchronization overhead. We have 3 main GPU approaches to compare. First is the standard neighboring pair reduction. Second is the recursive nested kernel with synchronization. Third is the optimized NoSync version. Here's the key difference. The regular nested version calls Cuda device synchronize inside the kernel. This ensures child kernels finish before continuing, but it is expensive. The no-sync version removes that synchronization call, much faster execution. But there's a catch. Race conditions can happen. Child kernels might not finish when we expect. The timing code uses millisecond precision. You can see the performance differences clearly. No-sync version is typically much faster, but correctness isn't guaranteed. This demonstrates the classic trade-off, performance versus safety. The nested approach still eliminates host device transfers. Everything stays on GPU. Each level spawns the next level. Reduction tree builds itself recursively. The running example here, we have process 16 blocks with 128 threads each, showing timing differences between synchronized and unsynchronized nested kernel approaches. Reduce integer file demonstrates 2 main approaches to parallel reduction in Cuda. We are summing arrays of integers here. First approach defined in reduced neighbor and reduced neighborless is neighbor pair reduction. Basic version has high thread divergence, uses modular operation to decide which threads work, very inefficient on GPU warps. The improved version reduces divergence, uses index calculation instead of modulo, much better warp utilization. Reduce interleaved is the second approach. This one is clever, starts with large strides and works inward. Better memory access patterns, less thread divergence overall. Then we get into series optimization. Reduce unrolling 2 for 8 are coming next. They are loop unrolling. Each thread processes multiple elements upfront, reduces the number of kernel launches needed. We have 2 times, 4 times, and 8 times unrolling versions. More unrolling means fewer blocks needed. Next level is warp optimization. Here we have reduce unroll warps 8, reduce complete unroll warps 8, and reduce unroll warps functions. Last 32 threads don't need synchronization. They execute in lockstep naturally. Can manually unroll these final steps, uses volatile keywords to prevent compile issues. Complete unrolling takes it further. Manually unrolls specific block sizes. Template versions lets compiler optimize away branches. All versions produce the same sum result. Performance differences are dramatic though. The code tests everything with millisecond precision timing. The running example here process over 67 million elements with 256 thread blocks, comparing all reduction approaches from basic neighbor pair to fully optimized template unrolling. Simple device query code file queries the GPU to get basic hardware information. It is very useful for understanding the device capabilities. The main function here is Cuda get device properties. It takes a device property structure and device ID returns all the hardware specifications. While querying device 0 here, that's the first GPU in the system. The program prints out key hardware details. Number of streaming multiprocessors comes first. These are the compute units on the GPU. The memory information, constant memory is the only fast memory. Shared memory is per block fast storage. Register count tells us storage per block. Warp size is always 32 on current GPUs. Maximum threads per block is important for kernel design. Usually 1024 on modern cards. Threads per multiprocessor shows total capacity. Warps per multiprocessor is calculated value. Just divide threads by warp size. This info helps us optimize kernel configurations. Memory constraints affect algorithm design. Thread limits determine block sizes. Simple but essential tool for Cuda programming. By running this file, it displays complete hardware specification for the first GPU, showing multiprocessor count, memory limits, and threading capabilities to guide kernel optimization decisions. Simple divergence code file demonstrates warp divergence and its performance impact on GPUs. We have 4 different kernels that do the same calculation but with different branching patterns. First is math kernel 1. This one creates maximum divergence, uses thread ID mod 2 being equal to 0 to decide the branch. Every other thread takes a different path. Within each warp, half go one way, half go the other. GPU has to serialize this path, very inefficient. Next is math kernel 2. It is a smarter approach here. It uses thread ID device divided by warp size mod 2 being equal for branching. This groups threads by entire warps. All threads in a warp take the same branch, no divergence within warps. It is much better performance. Then we have math kernel 3. This tries predication to avoid branching. Uses Boolean variable ipred to control flow. Still has some divergence issues though. To separate if statements still cause problems. Finally, math kernel 4 uses speed operations, similar to math kernel 2 but with bitwise operations. We also have warming up use function. It removes GPU initialization overheads. It is the same logic as math kernel 2. The key lesson here is warp alignment. When all 32 threads in a warp take the same branch, performance is optimized. When they diverge, GPU serializes execution. The running example here runs with 64 thread blocks, processing 128 elements, showing timing differences between highly divergent math kernel 1 and warp aligned math kernel 2 approaches. Some matrix code file implements matrix element-wise addition on both CPU and GPU. We are comparing performance between host and device execution. First, we have initial data function. It fills matrices with random flow values. Range is from 0 to 25.5 using bit masking. Next is sum matrix on host function. Standard CPU implementation here. Nested loops iterate through rows and columns. Pointer arithmetic move through matrix elements. Pretty straightforward sequential approach. The GPU kernel is sum matrix on GPU 2D function. It uses 2D grid and 2D block configuration. Each thread handles one matrix element. Thread coordinates map directly to matrix indices. Global thread ID calculations uses IY times NX plus IX for linear indexing. Boundary checking prevents out-of-bounds access. The running example here processes the large matrices using 16 by 16 thread blocks, showing timing comparisons between sequential CPU addition and parallel GPU computation with 2D thread organization. And we can see the GPU calculation is much faster than CPU.